Hi, and welcome to a quick history of atomic theory. On this page you can see a timeline going back to about 500 BC or so, and the people that are listed, we'll talk about some of those throughout this, but not everybody. So some old guys, some new guys, we'll see what we can find out. All right, before we get started though, we talked about models in class, and you did that model where you dropped the beans and the peas on the floor and marked where all those were. And the only reason we could do that lab is because some of these people we're going to talk about today have done other research and came up with other inferences based on the observations that they saw. So depending on what people find out in their experiments, our model of the atom is going to change over time. As technology gets better, we've been able to make more and different observations, and therefore we can make different inferences from those. However, in order for you to actually see something, light bounces off of it and bounces into your eye, and then your brain interprets that. However, we will never actually be able to see an atom with the light the way we normally see things, because atoms are smaller than the light waves. However, there are ways that we can bounce other things, such as electrons, in an electron microscope, so that we can have an image that's displayed because of what the electrons do. But anyway, so our models are always going to be an inference based on the reaction of how things react to the experiment that we happen to be doing at the time. So the atomic theory has evolved over time because of an increase in knowledge and the technology in which to test these things. So let's go back and talk about Aristotle and Democritus. Aristotle, most of you have heard about, and he theorized that all matter was made up of the four elements of air, fire, water, and earth. And you probably have heard this, just, I don't know, in a history class or something. However, Democritus actually, I think, they weren't, I should have looked this up, but I don't think they were actually alive at the same time. They might have overlapped a little bit. But Democritus came out with the idea that all matter was composed of tiny, what he called indivisible particles. And he called them atoms because atoms, I think, means indivisible in Latin or something. Anyway, and he was called the, quote, laughing philosopher, because he, unlike Aristotle, didn't have, really famous teachers and students. He wasn't quite as respected as Aristotle. He liked to have a good time and would always be making jokes. So even though we now know that Democritus was correct, the ideas of Aristotle actually were more respected, and therefore his ideas were more influential for over 2,000 years, simply because of the way he presented himself and his material. So it's just interesting to think about how personality played a role in that whole history of an atom thing. Anyway, so now we're going to jump ahead. We're at 400 or 500 BCE, and now we're going to jump up to around 1803 with John Dalton. So he was the first one to say, I think Democritus might actually have a point here. And so he came up with what we call the billiard ball model, that atoms are solid and indivisible. Now, his experiments were a little, I don't know, confusing, I guess. Although he did do experiments, a lot of it was still just based on philosophy and thought and that kind of stuff. So, anyway, he did these experiments, and this is what he came up with. All right, so here are the 5 parts of his proposed billiard ball model. All right, number 1, all matter is made up of indivisible atoms, which we can, trace that all the way back 2,000 years earlier to Democritus. All atoms of an element are identical and unique. Now, that sounds a little confusing. What it means is all atoms of an element are identical to each other, but different than all the atoms of other elements. Okay, so they're identical to each other, but different than any other atom of and different element. All right, there it is. Each element has different atoms. And he came up with the term compound, which are combinations of two or more atoms. And he talked about these specific ratios, and we're not going to go into that in any detail because we don't need to. Suffice it to say that you know that the chemical formula for water is H2O, and it's always in a ratio of 2 hydrogens to an oxygen, and that's always true. And he was the one to first propose this idea. And he also came up with the idea that when chemicals react with each other, what they actually do is atoms are rearranged and become something different. So it was pretty big step, and we could even look at it as a step backwards if we wanted to. But anyway, so that's the first. John Dalton was the first person to study or to come up with these things about the modern atomic theory. All right, and we still believe all these today. All right, he also came up with 2 laws. The first one you've heard of, the law of conservation of mass, which states, just like the law of conservation of energy, atoms do not appear or disappear during reactions. They can all be accounted for. Oops, sorry. So we're still on conservation of mass, which means mass cannot be created or destroyed. It can only rearrange itself into other materials. So you can state it just like you do the law of conservation of energy, except you replace the word energy with mass. This law of constant composition we're not actually going to get into, but again it refers back to the H2O example I gave earlier, in that a particle substance is always made up of the same number and type of particles. So H2O is always 2 H's and an O. It can't be anything else, and if it is something else, then it's not water anymore. So let's move on. So that's John Dalton. J.J. Thompson. He was the person who discovered the electron. See, remember the billiard ball model is atoms are solid, indivisible pieces of something. Well, J.J. Thompson came around and said, I don't think so. I actually think they have different parts. And he came up with this thing called the plum pudding model. And so you can see that picture over there with it looks like a cake or a Christmas cake or something. Pudding is the word that's used, or was used, I don't know if it still is, in Great Britain to mean any dessert. So a plum pudding was like a fruitcake. And he came up with the idea that there are negative charges embedded in a positive matrix. So if you think of chocolate chip ice cream, for example, the chocolate chips would be the negative charges and the ice cream itself would be the positive matrix. That was his vision of what the atom looked like. So if you look at the next picture below the cake, here's a picture of his plum pudding model where the orange color is the positive matrix and the blue dots are the electrons. Now, he figured this out doing an experiment using this thing called a cathode ray tube, which is that green glass tube at the very bottom of the slide. And we actually have one, and we're going to go over, and I'll show you this experiment in class. But anyway, so let's go and see what he came up with. What he said was that electrons are contained in all atoms. So what happened is he set an electric current going through a cathode ray tube, and he brought a magnet close to the cathode ray tube, and that stream of particles that was moving across the cathode ray tube actually was bent by the magnet, which means it was, well, in our case, I believe it's repelled by the magnet. Knowing that the side of the magnet that he was putting next to the cathode ray tube was also negatively charged, knowing that like charges repel each other, he was able to infer that the negative side of the magnet was repelling, well, he was able to observe that the negative side of the magnet was repelling the beam, which means the beam was made up of some sort of negatively charged stuff. Okay. Well, they also knew that atoms are neutral when they're found in their pure state. So, if there's a negative coming out of them, then there has to be some sort of positive that counteracts that negative to make it neutral. So this is where he came up with the idea of this positive pudding, that these electrons are in, the negative electrons, which are free to move, are buried in this positive matrix, this positive stuff. All right. So atom is neutral, so there has to be something to balance the negatives, and that's where he came up with this whole idea of the positive matrix. Very clever, brilliant experiment, and it's a cool one, and we'll show it to you in class. So J.J. Thompson discovered, or yeah, I guess you could say discovered electrons, and he was able to do this by making observations using the cathode ray tube and making an inference based on those observations. All right, so now we move a few years ahead to 1911 and Rutherford. Now, Rutherford did this brilliant experiment called the gold foil experiment, and we will actually show you some video of this in class. He was able to actually make 3 significant inferences based on what happened. So if you look at the black and white diagram above, that big circle represents an atom, and the arrows represent these things called alpha particles, which are basically 2 protons and two neutrons bonded together. So they're kind of like a nucleus. But anyway, so alpha particles, he was shooting them through atoms. And what happened was most of them, as you can see from that black and white drawing, most of the alpha particles went straight through. However, some of them, you can see, were deflected from their original path, coming in and then going off at an angle. And some even did something that appeared as though they hit something and they came back from the direction they first were shot out at. So he was able to make 3 inferences. First, he said that the nucleus is massive. And by massive, he means having a lot of mass. Not necessarily big, but just having a lot of mass. Well, how was he to figure this out? Well, the alpha particle that bounced back, if it had hit something that was less massive than itself, then it would have kept going straight. But you know, if something small or light hits something that's big and heavy, it's going to bounce back. And he knew our alpha particles were considered heavy, so when they hit something, they bounced back. So he was able to say the nucleus itself has a great deal of mass because it caused that alpha particle to bounce backwards. All right? And here the alpha particles, 2 protons and 2 neutrons. All right. He also was able to say that the nucleus is positive. Now, if you look back at what an alpha particle is actually made of, it's 2 protons, so 2 plus charges, and 2 neutrons, which don't have any charge at all. So this alpha particle is a positively charged thing. And he knew at the time that like charges repelled, and some of the alpha particles, when they were shot in, were deflected off course. Not because they hit anything, but because, as you know, when like charges, if you've ever tried to put the same side of a magnet together, they don't touch, they push against each other. So what he inferred was that, all right, well, in order to send an alpha particle off course, it would have to come into proximity of something with the same charge. So 2 positive charges are coming close together, and the lighter one, in this case the alpha particle, gets deflected from its path. All right? So the nucleus repelled the positive alpha particle. So that was the observation. The inference is that the nucleus is positive. His third inference is that a nucleus is tiny compared to the whole volume of the atom. If you look again at that top diagram, or actually any of the ones up there, you'll see that in the drawing, most of the alpha particles go straight through. Some of them are deflected, and even fewer of them actually bounce back in the direction in which they came. So the observation was that most of the alpha particles passed right through. And you'll hear on the video, it's not like, 20 pass through and 2 bounce back. It was like, 30,000 passed through and 1 bounced back. So it was a huge difference between those that went straight through and those that bounced back. So these 2 links are not going to work for you, but we'll go to them in class. All right, so now we know there are electrons based on what J.J. Thompson did with the cathode ray tube, and now we know there are the size of the nucleus, the mass of the nucleus, and the overall size of the atom. All right, moving on. Now we can talk about Bohr. Now, we've referred to Bohr models in class before. It's the sort of stereotypical nucleus in the middle of the atom and all the circles around it, which is where you find the electrons. And Bohr's model, still to this day, works beautifully to explain certain things about an atom. What you'll find as we do these, as we look at different models are good at doing different things, but there is no model that does everything well. So the Bohr model is good at looking at energy levels and the distance the electrons are found from the nucleus and all that. So what he discovered by looking at gases of atoms through what is this thing called? Spectroscope. And we'll try to get some of these in class. Sometimes people find them really hard to deal with and some of them really easy. So we'll give it a shot. But anyway, what he was able to infer, based on the fact that when he looked at certain atoms through the spectroscope, that they always, always, always showed the same colored lines. So if he looked at hydrogen, he'd get a certain color combination of lines. If he looked at mercury, it was something else. If he looked at neon, it would be something else. I mean, but they were always the same. So the evidence that he had was this light spectrum that he saw when he was looking through the spectroscope. Now, we first talked about this way back when we were doing forensics and we were looking at the flame tests, that the electrons can be made to jump to higher. He called them shells. We call them energy levels. So in forensics, when the metals were put into the flame, the energy from the flame caused the electrons to jump to higher levels. And then the electrons want, for lack of a better word, to really be where they originated. So they want to fall back. And as they lose that energy, they give off these specific colors of light. And we will talk more about that in class too, because we'll look at the spectroscopes. All right, now, where are we going after this one? Oh, yes, okay. So, in the mid-20s, 1920s, so we're pretty current here. Of course, that was almost 100 years ago, wasn't it? Oh, my goodness. Anyway, Heisenberg and de Broglie. We actually have a animated video to show you that is actually very well done, and it's kind of fun to watch. So we'll look at that in class. But just to get a sense of what these guys did. Heisenberg's uncertainty principle says that you can't precisely know the location of and the speed or motion of an electron at the same time. If you know where it is, you don't know how fast it's going, and if you know how fast it's going, you can't know where it is. And just the very act of trying to observe the electron is going to change how fast it's going. It's very confusing and kind of interesting to contemplate, I guess. So what this does is it leads to this sort of cloudy view of the electron, which is what you guys sort of created when you did that drop the dried peas as electrons experiment. It's all about areas of probability. And if you look at that black picture there over to the left, you can see that there's a high, if you looked at the little specks of light, blue light, as areas of probability, then the area of probability right near the nucleus is significantly higher, or not the area, if each dot of blue light represents the probability of finding an electron at that site, then you can see the probability of finding an electron close to the nucleus is much higher, and as you get farther and farther away from the nucleus, the probability gets less and less. And that's where this whole sort of electron cloud idea came from. All right, and de Broglie, and this is what you'll see this in the animation we show you, that electrons can behave both like as if they were particles, but they also behave as if they were waves. So this is this wave-particle duality, I think is what they call it. And if you look at waves, and we have a demonstration that we can do this with, waves come in certain wavelengths, which are measured from probably the top of one wave to the next. And they also come, and you can only get so many waves in a certain, distance. And we should have this rope demonstration that we'll do. And as you go from one wave to two waves to maybe even three waves, the way the rope behaves in between that is quite chaotic. So what that implies is that electrons can only be at certain distances from the electron. Anyway, wait till after you see the animation. It'll make more sense to you, I think. So this quantum mechanical model, which is the current atomic model, I guess, it takes into the account this whole idea of uncertainty and the probability of finding an electron at any given spot, and it also takes into account this whole idea of the electrons moving as waves as opposed to being strictly particles. So these regions of probability, which again is what you made when you did the P experiment, those are called the orbitals. So an orbital is an area of probability where you would more likely find an electron. Anyway, there's a couple other links we'll show you with that as well. Some image credits, and there you have it. So in class, if you could bring in your completed notes, jot down any questions that you might have. We'll go over some demonstrations, we'll show you some videos, and you'll have a great understanding of the history of atomic theory. Thanks for listening. Bye.